So where were we? So we were in the middle of this theorem. So theorem. Given a power series, which we wrote like this, right? The sum k equals 0 to infinity ak z to the k. Inside its radius of convergence. Oops. It is differentiable, i.e. forms a holomorphic function. All right. So we got quite far into the proof. What did we do? We defined various things, right? So we defined the Sn partial sum like this, right? Which was the sum from k equals 0 up to n, ak z to the k. And we defined, I think we defined f to be this power series itself. Okay, z to the k. We defined the error from the partial sum, right, which was just, well, the function take away the partial sum, which is the last terms of the series, okay, like this. And I think that's all that we defined, right? And then we were considering this thing. So we were considering f of z plus h minus f of z. We also defined g to be the derivative. So g of z is the sum from k equals 1 to infinity k a to the k z to the k minus 1. So we defined this thing like this, right? And we broke this up into various little pieces, you know, using these various devices. So the first thing we did was to write this quotient in terms of En and Sn, yeah? And then we wanted to, well, I'll just write it. It's rather easier to write it than to say all these words. So what did it do? We wrote Sn z plus h minus Sn z over h, and then the actual derivative. And it's not hard to show that this thing will be small because this is just a polynomial, it's differentiable. And then we had Sn prime of z minus g of z. Again, this is obviously controllable. And then we had this thing, En of z plus h minus En of z over h. Yeah? And we got to the point of estimating, or trying to estimate this thing, yeah? And we estimated the following. So we estimated that this thing, k minus z to the k over h itself, this thing, absolute value, was less than k r to the k minus 1, where r is the radius of convergence. So this is where we were. This is where we were. Okay, we're going to use this to estimate this guy right here. Yeah? So notice this, that this guy, absolute value of En z plus h minus En of z over h, this is going to be less than or equal to the sum. So we're summing from k equals n plus 1 to infinity. Now maybe unmute yourselves, because I'm not going to be able to hear very much anyway, and all I'm hearing is weird static. So sorry, start again. Now mute yourselves and then unmute if you want to try win the lottery and speak to me and see if it goes through. So mute yourself and just unmute when necessary. All right, so this thing, yeah, just using the definition, is going to be less than the absolute value of all of these coefficients, right? Ek, yeah, and then z plus h to the k minus z to the k. Say that. So this is the thing which we have to estimate, right? But we know that this is less than the sum k equals n plus 1 to infinity mod ak, and then this thing we've just estimated like this, k r to the k minus 1. Yep, like this. Cool. But this thing we saw from the previous proof is the tail end of convergence series, right? This is the tail end of a convergence series, because this r is the r we get from this Hallamard formula, right? So recall that 1 over r was the lim sup as k goes to infinity of the absolute value of ak 1 over k. Yeah, so this r looks a bit like a k. And that was strong enough to mean that these terms right here will be bounded by a geometric series, and therefore they converge, right? So we are fine to show that this thing here gets as small as we like, so long as we pick n to be as large as we like. And it's independent of our choice of h, because all we needed was that both z and z plus h belongs to the ball of radius 0, rate of r around 0. In other words, they're inside the radius of convergence. That's all that's needed for this estimate here that we talked about last time. So this part right here, we can actually control. We can actually get something out of. We can, more than that, we can make it as small as we like by taking n to be sufficiently large, and it's independent again of h. We just need h to be here. So z is somewhere inside our ball. We just need h to still be inside our ball. So there is some fixed radius where we can take any small h, and this will be true. Yeah. So in particular, remember we took an epsilon right at the beginning, or at least in the previous proof. So I should say it here. So for pre-chosen epsilon, there exists some capital N0 such that this guy right here, E capital N0, well, let's write it more generally, but we don't really need to, but let's write it more generally. E of z plus h minus E n of z over h, this thing right here, now, is less than or equal to epsilon for all n bigger than or equal to n0, just from this estimate. Yeah? So this guy, this term here, that we had to be concerned about, this guy is under control now. Yeah? So we're just going to work with our n0 from this point onwards, because that's going to be good enough for us. Yeah? So I'm going to use this estimate here, and we're going to take n0 inside all of this. Okay? Which means this will be less than epsilon, again, for all h, such that z plus h is inside the radius of convergence. So now we have to think about the other two terms. Yeah? And we have this thing to control and this thing to control. Let's control this thing, first of all. Well, what about this guy, Sn prime of z, right, minus g of z. Sn prime is just this polynomial given by the first n terms, right? So if we differentiate it, and g of z is what we get from differentiating term by term, if we take the difference, then we're just going to have the sum from n plus 1 onwards, right? So this thing is actually just equal to the absolute value of the sum from k equals n plus 1 onwards. Actually, let me do n0, because I said I'm going to take n0 of a k z to the k minus 1, right? And then the same estimate plays out here. We've chosen n0 such that this stuff is less than epsilon. So this is also less than epsilon. Yeah? Cool. So we've controlled two of our terms. Yeah? So this thing is less than epsilon. This thing is less than epsilon. And our final thing to control is this thing. And again, we've chosen n0. n0 is chosen. It's fixed. Yeah? And now we have the right to move h, because h, the only restriction is that it still remains inside the radius r ball of convergence, right? And this thing right here is just, for our fixed n0, is just a nice polynomial, right? So this is just the difference quotient. This is the derivative of the polynomial. And of course, this thing gets to be as small as we like as we let h go down to 0 for our fixed choice of n0. Yeah? So this thing, let me rewrite it here. This thing s n0 z plus h minus s n0 of z over h, okay, minus Sn prime of z. This thing is also less than epsilon for all, running out of space here, let me put this up here, for all h belonging to some particular radius around 0. I could probably put it here, right? Just by definition of differentiability. Yeah? Cool. So what that means is that this guy right here is also less than epsilon. Yeah? So putting these things together, we have that this thing is going to be less than 3 epsilon, right? For all h such that this is true, which I can just rewrite perhaps in this way, for all h absolute value less than delta. Yeah? Yeah? So what's that saying? That's saying that this quotient gets as close as we like to this holomorphic function, which you already know is a holomorphic function. We discussed this already. Yeah? And so as we take the limit as h goes to 0, then it is actually equal to this thing, which means firstly that this limit exists. Therefore, f is a holomorphic function. It is differentiable inside its radius of convergence, and its derivative is given by this. Okay? So we have what I claimed in this theorem, and this powerful thing is saying that inside the radius of convergence, power series behave just as nicely in terms of differentiation as polynomials. This expression here for the derivative is exactly what we'd get if we differentiated term by term if we had a polynomial. Yeah? So we have a very nice, strong, powerful result. Yeah, we can simply differentiate any function we can represent as a power series just term by term. So differentiation is way easier than finding the antiderivative. Nevertheless, there can be some tricky functions to differentiate there. You know, you have some difficult expressions with the quotient rule, whatever. Mix things up, have calculus students using the quotient rule, the chain rule in combination. If you have a power series, then differentiation is just a triviality. It's just a triviality, right? Cool. All right, so this says this, and the other cool thing it says is that we now have an even wider class of holomorphic functions. So we not only have the following function, the exponential function, or the complex exponential function. So if we consider this series, sum from k equals 0 to infinity, z to the k over k factorial, let's see what its radius of convergence is. So these coefficients are given by this thing. So if we try and take the kth root power of 1 over k factorial, right? So then the lim sup of this thing is 1 over r. Yeah? Lim sup of this thing is 1 over r. Yeah? So, let's estimate this from above. So this is the same as 1 over the kth root of k factorial, and we'd expect this to go to 0 as k tends to infinity, which would imply that the radius of convergence is infinity. So we're going to be bounding this from above, and we know that k factorial is k minus 1, blah, blah, blah. So in particular, it is bigger than what happens when we multiply k over 2 times k over 2. No, that's not what I want. It's bigger than k over 2 times itself k over 2 times, right? Because k over 2 of these terms are at least bigger than k over 2. So it's bigger than this, right? So if we take the kth root of k factorial, then it is going to be bigger than the kth root of this thing. Okay, which is going to be bigger than k over 2 to 1 over 2, which is square root of k over root 2. Right? Yeah, which means that this thing will be less than root 2 over root k. Okay? Because this thing is bigger than this thing. Yeah, so 1 over this thing is less than this thing. And this thing goes to 0 as k tends to infinity. Oops. So we do indeed have that 1 over r, which is the lim sup of this thing, which is actually just 0, implies that r is equal to infinity. Okay, so the radius of convergence of this thing is everything. It converges everywhere. So this thing, this power series, forms a holomorphic function. It's differentiable everywhere, and we are going to see what happens if we stick in just I times theta into this. So notice that if we put in the sum k equals 0 to infinity of I times theta to the k over k factorial, we can break this into this sum over the odd or the even. The sum k equals 0, infinity I theta 2k plus 1 over 2k plus 1 factorial, like this, and then the sum over the even, say m is equal to 1 to infinity I theta to the 2m over 2m factorial. And then what happens to this thing? So this is sum from k equals 0 to infinity. Let's pull out this I to the 2k plus 1, right? So what is I to the 2k plus 1? Let's put it over here. So I to the power 2k plus 1 is equal to I, and then I to the 2 power k, which is equal to I times minus 1 to the k. Yeah? So what we have here is going to be minus 1 to the k, put out the I all the way here, and then we're going to have just theta to the 2k plus 1 over 2k plus 1 factorial. Okay? And then from this thing, what happens? We're just going to have sum m equals 1 to infinity, and we're going to have minus 1 to the m, theta to the 2m over 2m factorial, like this. Yeah? And as you guys know, or as you people know, this thing is just going to be cosine of theta, and this thing here is just I sine of theta. So this is what we're going to motivate for the following thing. So we can define the exponential function e to the z, which is e to the x plus iy, in the following way: to be just e to the x, so this is the definition. E to the x, we know what it is, it's the exponential function. E to the I theta, we know what it is, it's defined. Okay, I should perhaps say, should perhaps write it like this. Write it like this. Cosine of y plus I sine of y. Yeah? So if we define it like this, then what we know? Then the above calculation is that we have this is given by this power series equals 0 to infinity I theta to the k over k factorial. Yeah. And if we just do this, e to the theta itself, or just e to the x, e to the x itself, then just from this thing, there's no imaginary part. This is just e to the x. Which is also just given by the power series, the sum k equals 0 to infinity x to the k over k factorial, as we know from just calculus, right? So what we see is that if we define it this way, then it actually agrees with the power series on the imaginary axis and on the real axis. And later we're going to see that if we define it this way, actually this power series actually represents e to the z everywhere. You know? But that we'll have to see later. What you can check pretty easily is that if you define this function like this, and this is perfectly well-defined function from the complex numbers of the complex numbers, then this thing satisfies the Cauchy-Riemann equations. Just check it, just do that calculation. However, that doesn't based on what I've shown you, that doesn't imply that it's holomorphic yet, because what I've shown is that if it's holomorphic, then it satisfies the Cauchy-Riemann. The reverse implication is also true, but that is harder. That can be done with the hypothesis that the function has got continuous derivative fairly easily, but in more generality, it's actually harder, perhaps quite a bit harder. So this thing, okay, is nevertheless. So we're gonna assume this thing, which we can't prove yet, is true. This thing actually is given by this thing. It is given by this power series. So this guy is an example of a holomorphic function, and we're going to try and understand what it does, and it does surprisingly dramatic things. So see if I can squeeze this in. Maybe I can squeeze this in here. So let's take a look at its behavior. Let's look at the complex plane here, and let's map it over here with the complex plane. Okay. Let's see what this function does. If we take a strip from pi to minus pi, and we map it with this guy, e to the z, let's see what it does. Well, if we take a line like this, so let's fix some x0, and let's take a line like this which goes through this strip, okay? So then we are varying the y from minus pi to pi, but remaining the x fixed, right? And then let's look at this definition. So if we do that, then the y is changing. Yeah, the y is changing, yeah, it's going from minus pi to pi, but the x is remaining fixed, right? So this thing, as we move along this strip right here, x0 is fixed, it's this thing, and this thing is just the unit vector in the complex plane rotating around from minus pi, which is over here, all the way to pi, right? That's all that we're doing. So we are going to get a circle whose radius will be like this, e to the x0, yeah? Because we will start right here, minus pi, and we go round and round and round like this. That's what it does. And if we do the same thing for some x0 over here, then we get a much smaller circle. And if we do the same thing over here, we get a much bigger circle. So these vertical lines are mapping onto circles. Yeah? If we take a horizontal line like this, so now the y is fixed, so it's y0, and we're going to have the x will be changing. Yeah. Then what happens? So y is fixed, so then this is defining the angle, okay? So this is the complex number part, or this is a complex number, and this is just a real number, right? Yeah? So as x varies, as x goes towards minus infinity, we go towards 0, right? We have e to the minus x for a very, very negative x. We go towards 0, and as x gets positive towards infinity, we go towards infinity. So then this blue line here is actually going to form this ray going out like this. So where this is where we go towards minus infinity, and this is where we go towards positive infinity. And then this thing here is going to be given by angle y0. Yeah? And note in particular that at the crossing point of these lines, this point right here, sure enough, they are crossing at 90 degrees. The angle is being preserved, which is what we know has to happen for holomorphic mapping. And what this little calculation also shows is that we are mapping this entire strip onto the complex numbers except 0, right? So we're mapping the entire strip onto the complex numbers except 0. Well, let's put that here. So E of z sends this strip, which I'm going to denote like this, so the real numbers cross product with, let's do it like this, I times minus pi. Pi, this thing is sent to the entire complex numbers, take away 0. No? Cool. But from this definition right here, if we consider the strip which we just get from moving up a little bit from pi to 3 pi, okay, then the same thing's going to happen, right? Because this expression here is periodic in pi, right? So whatever's happening here, if we move up by 2 pi from here, exactly the same thing's happening, right? So it's going to map this strip to the same thing, right? So we can cut up the entire complex plane into these horizontal strips of width 2 pi, and every single one of them is wrapped around the complex plane, right, in the image. You know? So this is a really crazy behavior. This is much more strange and complicated than z to any power k, which we can sort of visualize just by making a slit and then wrapping something around. This is taking the entire infinite horizontal strip and wrapping around the complex plane, and it's doing this in a holomorphic way, and it's doing this in a way which is differentiable at every single point. And later we'll see it's even more than differentiable. It's differentiable to any order. In fact, it has a Taylor series. It's analytic. Yeah. So very dramatic, strange behavior for a function that locally preserves angles everywhere and is differentiable everywhere. It's quite a surprise that such a thing exists, but it does, and it's not. These things are not particularly hard to work out. So we have this particular example of a strange complex, of an unusual, surprising holomorphic function. And note it also recovers the ordinary exponential function that we know, because if we just look on the real line, then on the real line, then this is the exponential function that we know, right? If y is just 0, it's just the ordinary exponential function. So this monster contains the guy that we know well from calculus, and it just contains it when we restrict what happens to the real numbers. It sends the real numbers to the real numbers. Yeah? So part of the familiar old exponential function we've known about for a long time is inside this guy. All right, we're going to talk about log functions and trig functions when I erase this board. Okay, so let's discuss more this strange function, what it does. So we've seen that it takes all these horizontal strips like this. So it's minus pi, 3 pi, and so on. And it maps them, wraps them all around the complex numbers, except 0. Yeah? So in particular, so this is z goes to e to the z. If we take some complex number here, say w, and we ask ourselves what gets mapped onto w, well, as we've seen, for any one of these strips, for sure it maps around the entire complex plane except 0. So in each one of these strips, we're going to hit this at least. In fact, we're going to hit exactly one time. It's kind of clear from our construction. In each one of the strips, there will be one guy that hits this, right? And because whatever's happening in the strip is happening on every strip moved 2 pi up, 2 pi down, for any multiple of 2 pi actually, then the same thing is going to happen here, and then here, and then here. So all of these blue dots, we mapped all onto w. So the inverse of e to the z is no longer going to be a one-to-one function, which it is on the real line when we do calculus. E to the x is a monotone function, satisfies the horizontal line test. It's invertible. We have the inverse is called natural log. no such thing happening here, right? But the inverse seems to have quite a regular structure. In fact, if we restrict down to some particular interval from minus pi to pi, then it will be invertible, right? Because there's only one copy happening there. So recall some notation. So given z inside the complex plane, then we can write z as mod z and then e to the I of theta for some theta, right? And theta is not unique because every multiple of 2 pi is also going to do this representation. But we can choose what we call the principal argument, which we're going to write like this. So arg of z is the one particular number which, like this, or it might be the other way around, which satisfies this, which is inside this interval. There's only one guy which will satisfy this, so that z is equal to mod z e to the I arg of z, right? That's the one representation of the angle inside this particular interval. And this thing we're going to define to be equal to arg of z plus 2 pi k for all k which are integers. So this thing is actually an entire infinite set of complex numbers. Sorry, this is an entire infinite set of numbers, of angles, right? So this is at least notation in Zill's complex analysis book, I guess somewhat standard notation. So let's try and understand what the inverse of e to the z will be, given that we have a fairly good picture of the way it behaves. So if we restrict to just minus pi to pi, then what happens? So if, let's call it, to give it a name, let's call it log of z is the inverse of e to the z restricted to this strip here, minus pi. Let's do the r first. Then what properties will it have? Then it has to have this property that e, let's write like this, of z has to be itself again, right? But then this thing is just given by e times the real part of this guy plus I times the imaginary part of this guy, which by definition of e, how we've defined it, is this thing, e of the real part of log of z, and then times e to the I, the imaginary part of log of z. So if we just take the absolute value, this thing is just a complex number of length 1, right? So taking absolute value, we have that mod z is equal to just e times the real part of log of z. And therefore, if we take natural log now, I mean real natural log from the real numbers, which we'll denote by log to the base e. So let's put over here, log to the base e is this natural log from real numbers to real numbers. If we do that, then what happens? Then we have that log to the base e, again, this is notation from Zill, is equal to this real part of log of z. So we understand what the real part of this function has to be, right? Just by taking absolute values. And now if we look at the direction of these complex numbers, right, in this guy, then the direction is denoted by this thing, right? So we also have that z is equal to mod z e to the I times arg of z, which is equal to this thing, right? So let me put this since. So from the line above, let's call this thing star. From a star, we have what? We have that imaginary part of z has to be equal to this thing plus any 2 pi k, right? Because actually, just write it out in steps. So we have from star and the fact we've just found out that mod z has to be this thing, we have that e to the I times the imaginary part of this thing has to be equal to e to the I arg z. Yeah? And the only way that's true, we could also write e to the little I arg of z. This implies that imaginary part of log of z is equal to arg of z plus 2 pi k. Let's write it like this, i.e. that's the same as little arg of z. Yeah? So, what that means we've completely defined what log of z has to be, right? Because its real part over here is given by this. So it's log the base e of mod z. That's what it does to the real part, right? And the imaginary part we've got from over there is this, which, as we know, is like this infinite set of real numbers, right? Arg of z is this infinite set of real numbers. Did I erase it already? No, here it is, right? Yeah, and let's compare it to a picture. Well, if we restrict this thing just to minus pi over pi, then it is indeed a well-defined function, and we would have this thing. For e to the z restricted to just one of these strips. Yeah? Because in this case, if we were restricting z to one of the strips, so the inverse is going directly back to the strip, then it is not arg plus anything else, it's just capital Arg by itself, which is by definition just in this strip. Yeah? So the restricted mapping from here to the entire complex numbers minus 0 is invertible by this guy. Yeah? And the more general inverse is not a traditional function. It's not a one-to-one or many-to-one function. It's a one-to-many function. It's a set-valued function. The general inverse is given by this. So better perhaps to have different notations for these two guys. Maybe I don't know. I will say log n and then put a tilde or something. Log e, c, and now we have this. So it's every z over here we have an entire infinite set. This is defining an infinite set, right? And that infinite set has its real, every number inside that infinite set has its real part is given by this, but the imaginary part changes, and it's exactly this picture here. It's exactly all of these dots right here, right? Because each guy is just moved up or down 2 pi I from the other. Yeah? So we recover in the language of maths what our picture tells us. Our picture tells us that that's what happens. If we consider all the images, all the z that map onto w, we get a thing like this, and then the language of math confirms it. That's actually what we get. So that is the log, the general log function. And again, it's a more complicated type guy. And interestingly, this is a very classical subject. This is 17th, 18th century math, and this is one of the origins of the theory of Riemann surfaces. So I don't know how much you people have studied a little bit about this, but you presumably heard of these things called manifolds, which are these sets in which are more general than arbitrary, just portions of space. They are sets that we define with a diffeomorphism from an open subset of some Euclidean space to some part of the set, and there's different diffeomorphisms that cover the entire set, and they act in a nice way across each other, right? So locally, we can describe it as being something like Euclidean space, but not globally, right? This was initially a kind of a concept that was somewhat difficult, took a while to develop. And one of the reasons for developing it was to try and understand things like this, because if we don't want to think about this as a function which is mapping one to many, if we want to try and understand this as a function that is actually one to one, then we can't map it back into the complex plane. We have to map it into something called a Riemann surface, which is just a complex manifold. It's a manifold where the charts are made up from analytic mappings from subsets of the complex plane onto that particular set. And I downloaded a picture from the internet like this. So this thing here would be something that would allow us to map with log from the complex plane onto a guy like this, where we wouldn't have the issue of having multiple values, because this thing would make sense. So this is a little bit off topic, but nevertheless, this historically is initiated the development of a lot of maths, that we had to stop thinking about just dealing with subsets of Euclidean space or subsets of the complex plane, but we had to define this more general object where we do analysis, where we do calculus, called the manifold, in order to make sense of things like this. Okay. All right, so that is the general expression for exponentials. Let's try and develop complex trig functions from this. So let's do the following. So what do we know? We know that e to the I theta is cosine of theta plus I sine of theta. So e to the minus I theta is cosine of theta minus I, because sine is odd, right? So we put the minus theta through, we pull it out. This. So if we add these things together, and we divide by 2, we just get cosine. Yeah? And a similar calculation, if we take e to the I theta, and now we subtract e to the minus I theta, right? Now the cosines are going to cancel, and we divide by 2i, we're going to get sine of theta. And that's going to allow us to define these functions like this. From the complex plane to the complex plane, we're going to find sine of z from this thing to be e to the z, or e to the I of z minus e to the minus I of z over 2i, and cosine of z to be e to the I times z plus e to the minus I times z over 2. And since e to the z and therefore e to the iz and e to the minus iz are perfectly well defined holomorphic functions, we're just subtracting 2, dividing by a number, just like multiplying by a number. So this thing is a holomorphic mapping as well, just because what we know about holomorphic mappings, we can add them, subtract them, multiply by a constant, all that stuff. And this guy too. So this thing, these things are perfectly good holomorphic mappings. They're defined everywhere, differentiable everywhere. And if we restrict down to just theta being between minus pi and pi, then these guys give us back, well, in fact, if we just restrict theta to be on the real line, these guys give us back ordinary sine and cosine. So these things are deformations of the complex plane preserving angles, right? So we have the complex plane over here, it's mapped to the complex plane over here, right? And if we just look at let's put this picture here. If we just look at what's happening on the real line, then we recover our ordinary trig function. So if we think about this thing, z goes to sine of z. Okay, this is deforming the complex plane. Yeah? It's deforming it in a locally angle preserving way. But if we just take a line like this, see what's happening here, then it is actually just mapped to minus 1 to 1, like this. The real line is mapped to here. Okay, and the behavior of this guy on just the real lines is just our sine function, right? So what this means is that these common trigonometric functions that you're familiar with for many years now, you learn in middle school, I guess, and indeed mathematicians were familiar with for a long time before the discovery of complex analysis. They are just a part of another function, a more general function, which is actually acting in a nice way, in a completely nice way, from the complex plane to the complex plane. So all this stuff of studying trigonometry, all this stuff that you learned, you're just studying the behavior of this guy on the real line. Yeah? You're just studying the behavior of a little bit of this more general function. It is just a slice through these particular guys. It's just like I feel like saying like they're like shadow of some bigger thing, and that must have come as quite a surprise to the early mathematicians who discovered this, because you would think you'd know everything about what sine and cosine, they seem fairly simple things, but no, all along you were just looking at just a piece of something much bigger, much more general. And this guy, it's holomorphic, but as you can guess, given how wildly non-one-to-one this guy is too. This guy is also wrapping the complex plane many times around in the image, and so it's actually a kind of a quite a interesting guy. It's quite a complicated, not complicated, but quite a rich, has quite rich structure, this holomorphic function. It is richer and more complicated than you might think. And it's kind of like a little bit of a taste of what happens more and more in higher math, that you think you understand something, you think it's some mathematical object that's been studied for a long time, and many properties about it, and within that area you can prove these properties with this collection of techniques, and then later it's discovered that that thing is just a special case of some other object, and the other object is way more rich and has a lot more structure than the thing that you were studying. And all the stuff that you know is just a special case of the stuff about the more general thing. And you were just looking at a slice of the real story. You just had you were just looking at a tiny kind of, like, this is just literally a slice of the action here. So it's kind of cute the way that you can see this already in this field, that these common, easily understood or well understood things, trig functions, are part of some other thing. And the more you study math, the more you'll find that. And there's more you'll find that still continues, that we find that things that we think we understand because of some stuff within some context is actually just part of something else. All right, let's see how I am for time. I will wrap it up at this. So next class we will do an example. We'll calculate an example of considering we'll do an exercise to illustrate the kind of structure of this trig function, and that'll be it for understanding trig functions, understanding or studying examples of complex functions. And then we'll start to develop develop the main theorems for holomorphic functions, and develop the theory. Now that we know that there is a wide class of functions, now there are an actual rich class of functions to build a theory on, we are going to start to develop the theory and prove more and more restrictive things about them. All right, so that's it for today. See you all on Tuesday.